see, how do I get that out? Okay, let me see if I can kill the thumbnail video. Very good. Okay, so I'm going to be speaking on a subject that's based on work that I did. Well, first, let me thank the organizers for inviting me to talk at this conference on quantum gravity, which is a subject after my own heart that I've spent my life working on. I'm going to be telling you about some work that I did a year and a half ago with Shunpei Miao and Nick Tsamis, and some much more recent work with Irini Kazdagli and Martha Loa Kalzenzon, and with Boran Yezylyard. And let's see here. I'm not able to get the thing to advance, so I think I'll do it manually.
You might want to click into presenter mode. There's an icon down at the bottom.
How does one click on presenter mode?
Down on the bottom row, just before what looks like the volume, on the right hand side, right of that, a couple more.
Yes.
There's a presenter. I think that's presenter mode. Yeah.
Oh, very good.
Yeah, there we go. We have your full
okay.
screen now. That's good.
So the idea behind this is based on phenomena that all of us are well familiar with, and that was indeed the subject of the last talk too, and that's the inflationary production of scalars and gravitons. I'll remind you all that the geometry is essentially homogeneous, isotropic, and spatially flat. Hubble parameter is a dot over a, and first slow roll parameter is minus h dot over h squared. Inflation is defined as positive expansion with first slow roll parameter between 0 and 1. And the special case of de Sitter is epsilon equals 0, which makes h exactly constant and a grow like e to the ht. And we all know that inflation produces lots of scalars and gravitons. If you work in single scalar inflation, then the number of inflatons that gets produced can be related to the measured scalar power spectrum, and it grows like crazy because it's got that factor of a squared. The number of gravitons is actually more general than just for single scalar inflation, and it can be written in terms of the tensor power spectrum times, again, something that grows like a squared. So this is what creates the power spectra. And of course, these particles don't just sit there. They will interact with themselves and with other particles. We might argue about whether that's a big effect or a small effect. But what I'm really interested in is that it's a secular effect, because you can see the numbers of particles keep increasing. And that means that more and more of them are around to interact. And if we take, we can see that if we look at loop corrections in a very simple scalar model of a massless, minimally coupled phi to the 4 on de Sitter background, and take the expectation value of the stress energy tensor. It of course takes, by the way, this is not the inflaton, this is just a spectator to de Sitter inflation. It takes the perfect fluid form with pressure P and energy density rho. And if you explicitly do the calculation, the one loop term is easy. You have to work pretty hard to get the two loop contribution, the order lambda contribution, and you see that it has these logarithms. Actually, it has a logarithm of a squared and a logarithm of a. Leading logarithm order in this theory is if you're at lambda to the n, then there would be up to 2n logarithms, and lower powers are subleading terms. So for example, the logarithm squareds in the two loop results are leading logarithms. The logarithm of a is a subleading logarithm. Okay, well, you get these things whenever you do calculations that involve essentially massless minimally coupled scalars, also from gravitons, which obey the same, whose mode equation is the same as the massless minimally coupled scalar. Scalar effects are much, much simpler to do. You can do them in an afternoon. Graviton effects are much harder to do. So if you do that in, say, something like electromagnetism, it could take a year to do the calculation. But gravitons can do things which scalars cannot, and they're also generic. So it doesn't depend on, we believe that general relativity is the low energy theory of gravity. So nobody can say, gosh, that's the wrong model of gravity. It's certainly the right model of gravity. And they can do things that scalars can't do. And that's because they carry spin, and that provides an interaction which doesn't redshift. And very many fewer of those calculations have been done because they're much harder to do. But I'll review two of them. One of them is gravity plus electromagnetism, which was Katie Leonard's thesis problem, and then was used by, Soyun Park, Tomislav Prokopets, and I to calculate the corrections to the Coulomb potential. And they take this form of a de Siderized version of the famous flat space result that goes like Q over R, and then a term that's a de Siderized version of a well-known flat space quantum gravitational correction that would be G over R squared, and then a new term that you only see in an expanding universe, which involves the new dimensionless parameter GH squared. And this one sees the secular growth that I was talking about and also grows with R too. Another calculation of the field strength of a plane wave photon was done with Wang Chonglong, and that also has a secular logarithm. Pure GR was done with Nick Samus and Lin Tao Tan, and there we calculated again the mode function, just like here, and the Newtonian potential. And because gravity, when it interacts with itself, involves more graviton propagators that carry the logarithms, you get more logarithms. So you get two logarithms in the correction to the mode function, and up to three logarithms in the correction to the Newtonian potential. And the thing I want to draw your attention to is that the loop counting parameter, GH squared, is a small number if you accept the bounds on the coming from GH squared on the tensor to scalar ratio. GH squared must be 10 to the minus 10 or smaller, but logarithm of A can get bigger, arbitrarily, depending upon how long you wait. And so eventually, although these things start out as very small effects, if you wait long enough, eventually the logarithms of A will overwhelm the factors of GH squared, and it doesn't even take all that many e-foldings if you have a logarithm of A to the third power. And of course, you'd like to know what happens later on after the breakdown of perturbation theory. And I'm going to tell you how to figure that out by summing the series of leading logarithms. And I especially want to know whether or not there's some effect that survives to late times. And so I'm going to need a way to do that, not just in de Sitter background, but for a general A of t, which experienced primordial inflation and then went to something like our current universe. And that's the origin of the title, Remembrance of Things Past. I want to see how it remembers the fact that it underwent primordial inflation. And there is a technique for this that basically almost works. I don't know if you can see if this bar is affecting everybody. It was developed by Alexei Starobinsky. It's a stochastic formalism. And it works for scalar potential models. So, for example, like this model in terms of the scalar phi with a potential. For example, the first calculation that I presented to you was a lambda phi to the fourth interaction, and that got a energy density which, from explicit calculation at two-loop order, looks like that. You could carry it out as high up as you had patience for. But using Starobinsky technique, you can not only predict what you would get at leading logarithm order for each order, you can also sum it up. And there's the summed up result due to Yokoyama and Starobinsky in 1994. The way it technique, so this formalism just blew me away. And I set out to figure out why it was true. The way it works is you replace the Heisenberg field phi with a Langevin equation for a stochastic field script phi. So there's the exact Heisenberg field equation for capital phi. The Langevin equation that you replace it for is much, much simpler. And script phi 0 dot is the stochastic jitter term, which comes from this mode sum, where it's got the free field creation and annihilation operators, but truncated at horizon crossing and only with the leading infrared parts of their mode sum. So this is a completely different theory than capital phi. It's a stochastic field because it actually commutes with itself for all space-time points, but correlators of script phi produce exactly the same leading logarithms of capital phi to all order. And like I say, you can also get the late time limit when it actually approaches a late time limit. And here's that Starbinsky-Yokoyama result. So the way that is you first integrate the exact field equation to Yang-Feldman form. Of course, when you hit this with 1 over box, you get a 0 of box. That's the free field mode sum. And here's the interaction written with a retarded propagator in the form of a commutator of 2 free fields. And if you just iterated that, that would generate the interaction picture representation that people who do field theory are used to. The key insight that makes this proof work is that in order to reach leading logarithm order, it has to be that each of the phi naughts contributes a leading logarithm or contributes a logarithm. Those logarithms come from the infrared sector of the mode sum. And what that means is that you'll change the theory completely if you truncate phi 0 to be just the infrared modes, but you'll preserve the leading logarithm results. And when you do that, you get a equation which, if you take its time derivative, is just exactly Starbinsky's Langevin equation, and Starbinsky's stochastic jitter script phi dot is just the infrared truncation of the free field mode sum truncated to only infrared modes and with the mode function truncated. So this is amazing. I mean, this is just a tribute to Starbinsky's genius that he could get this, and it's a wonderful tool. Unfortunately, it doesn't quite work for gravity. And the reason why is you can see from the key step in the proof. It's that in order to reach leading logarithm, every single free field has to contribute an infrared logarithm. When you have derivative interactions, such as you do with gravity, then that's no longer true. You still get large logarithms. I showed you some explicit results, but the differentiated free fields don't contribute them that. And that means that you can't know which ones in the final expansion are going to be differentiated and not, because you would have to iterate it to all orders. And you can't just truncate the free field at the level of the field equation. So that has frustrated application of this wonderful formalism to quantum gravity. It turns out that you can apply it to quantum gravity, and I'll tell you how to do that. Let's see if I can the thing to advance. I'm not able to get it to advance. Oh, David, what do I do here?
Well,
I'm not able.
Yeah. Usually you can just use the arrow keys or whatever. If you click on the presentation and then, yeah.
Hey, there we go. It works. Thank you. So rather than beat my head against quantum gravity, which has all the indices and also has a complicated gauge issue, I'll apply it to nonlinear sigma models, which are much, much simpler, but have the same kind of derivative interactions. Nonlinear sigma model is just a scalar field, but with a function of the fields multiplied by it. Here's an example. They also show large logarithms when you work in de Sitter. And the way that and so they also suffer from the derivative problem. The way that you apply it is you just integrate out the differentiated fields in the field equation. So there's a differentiated field, and this guy, when it acts, would give another differentiated field. You integrate them out under the assumption that the scalar is providing a background which is constant. And you might say, gosh, that looks really complicated, but in fact, it's trivial. You can see it's trivial from the Lagrangian. If you just set phi equal to a constant, then all that would do is to multiply the free propagator by a field strength. And so the exact field strength that you could get if you were doing it in a constant scalar background would be the free scalar propagator and then divided by this function of the background fields. So when you do that, you can define an effective potential, which is just obtained by integrating out, like I say, that fields. And when you do that, lo and behold, what you've got is something that could be interpreted as a scalar potential model. And remember, Starobinski's technique works for scalar potential models. So if you integrate this thing and get the potential, you get a logarithmic potential. And we can then study it using Starobinski's form. We have to be a little bit careful because the original field equations had those factors in it. But when you do that, then here's Starobinski's Langevin equation applied to that model. And the VEV of the field capital Phi shows a classical slow roll, or classical, actually fast roll, down the logarithmic potential accelerated by stochastic jitter. And if you just eliminated the stochastic jitter, you can solve exactly for what the classical behavior would be. And there it is. And then the stochastic jitter accelerates its behavior because it's, of course, easier to fluctuate down a potential than up a potential.
Richard,
okay, so
may I ask you
a question?
for the interruption, if you don't mind?
Go for it.
Richard, I have a question. So this theory looks like if I do filter definition, I could define a new field, which is actually 1 plus lambda divided by 2 phi multiplied with phi, and then it will be just a free field.
You know, you're right about that. So if you see this first line here, I didn't mention it, but you're right, and I'm sorry, I should have mentioned it.
Yeah.
This thing is all single field nonlinear sigma models are equivalent to free fields. And that means that they have a unit S matrix. And this is, by the way, another spin-off of this thing that's an important point, I think, relevant for those people who believe that the S matrix tells us everything that we might want to know about quantum gravity. Believe that this is an explicit counterexample. So this thing has unit S matrix, and you can see it explicitly in the correlators and everything. Nonetheless, it has an interesting evolution of the background, and it has interesting kinematics as well. Having unit S matrix just means that there's no interaction between single particle states, but it doesn't tell you what the masses of the single particle states are. And in fact, in this model, they evolve, and you can see it explicitly. So there's no question that it's true. You can actually explicitly perturbatively calculate it. In fact, the easiest way to do it is using exactly that field redefinition. So that's all true, but I think irrelevant. And this is, I would say, an example, a counterexample to those who believe that the S matrix can tell us everything in quantum gravity. I think we'd all love to know what the background is doing in quantum gravity applied to cosmology, and you will not be able to get it from just the S matrix.
Thanks.
So I hope that answered your question, and thank you for asking it. So, like I say, this brilliant formalism developed by Starobinsky does get almost all the logarithms, the leading logarithms, but it misses some. These are logarithms that wouldn't be present in scalar potential models. They come from the ultraviolet. They come from the fact that primitive divergences just go like 1 over d minus 4 without a d-dependent factor of a, whereas counter terms, because of the square root of minus g in dimensional regularization, always go like a to a d power. So when you subtract them, you're going to get a logarithm of a, finite logarithm of a, and those terms are present also. So that would not happen for scalar potential models, but it does happen for nonlinear sigma models and for quantum gravity, and we can see it explicitly. And we actually have a way of calculating it. So those logs are captured by the renormalization group. And I'll deal with that in another model, nonlinear sigma model, which involves two fields, a field capital A and a field capital B. And to renormalize the 1pi 2-point function of B, you would need two counter terms, a box B, and then an R, d mu B, d mu B. The box B term, you do need it, and we worked out explicitly what all those constants are, but it turns out that it has nothing to do with large logarithms. The one that has to do with large logarithms is this one. And that could be viewed, if you were thinking a little strangely, as a curvature-dependent field strength renormalization, right? See, this is just the initial kinetic term. So if you do that, you just forget about the higher derivative one, and look at that, and then plug that into the Kalam-Zemanzik equation, you indeed would predict some large logarithms. And we did the calculation, we did the math for all the single field model and all the double field model. And here are the large logarithms we calculated at 1 and 2 loop order. So we calculated corrections to the mode functions, corrections to the exchange potential, corrections to the expectation value, and corrections to the square of the field variable for all these models. And the stochastic, the ones which are explained by the stochastic formalism are in red. The ones which are explained by the renormalization group are in green, and all of them are explained. By the way, in the paper with Nick and Shunpei, this one was not explained, but Baran Yazelyurt just explained that one. And actually, Baran also Baran and I also showed that the beta function is 0, at least up to order lambda to the 5th. So I would say that that's neat, and that I think completely solves the problem of how to resum these large logarithms in nonlinear sigma models. Of course, the reason for doing this was because we wanted to apply it to quantum gravity, and you might think, oh gosh, that's impossible. But it turns out actually to be very simple. So remember, there's two things that you want to do. You want to get a curvature-dependent induced stress tensor and a curvature-dependent renormalization, and I'll show you how to do each of them. So the analog of keeping the scalar constant is to keep the graviton field constant. That is, you can formally rescale the metric as usual. You write G mu nu is equal to a squared times G tilde mu nu, where G tilde is eta mu nu plus kappa H mu nu. And then again, the analog of keeping the scalar constant is to make H mu nu constant. And you might, and the key step of integrating out the differentiated fields is, can you evaluate the propagators for constant H mu nu? Well, it turns out you can. It's easy. It turns out that that if G tilde, if the exact metric was a squared times G tilde mu nu, where G tilde was constant, then you can get the exact connection and the exact Riemann curvature, and you see it takes the locally de Sitter form, but with a slightly different Hubble parameter. So all you have to do is to take your existing de Sitter propagators, de Sitter graviton propagators, and replace H squared with minus G tilde upper 0 H squared, and that will do the result. And here's an explicit result. So take, for example, a massless minimally coupled scalar, how it would contribute to gravity. You would want to integrate out these differentiated scalar fields. And when you do that, you induce something which can be recognized as a negative contribution to the cosmological constant with a factor there that could become arbitrarily big if G lower 0 was approaching 0. That is, if it was basically generating enough stuff that it was falling within its own Schwarzschild radius. So I think that that is hugely interesting and possibly very significant. How about renormalizations? How about the large logarithms that come from curvature-dependent renormalizations? Well, the two counterterms that you need at one loop order in this theory, that is massless minimally coupled scalar coupled to gravity, would be c squared and r squared. The c squared is, again, a fundamentally higher derivative counterterm, just like the box B term, that plays no role in generating large logarithms. But the r squared term can be broken up. Let's just do a little algebra and write it as r minus d lambda. Of course, that term vanishes at the background, so that goes like h squared. And then then the feed down terms, one linear in r and one without any r's at all. This second one can be viewed as a cosmological constant dependent renormalization of the Einstein term, right? This last one could be viewed as a renormalization of the cosmological constant, but because it has a factor of d minus 4, it makes no contribution. So in fact, you can do just exactly the same formalism for gravity, and there are still some things that we need to work out, but looks like it's good. It looks good. Okay, so what I'm going to tell you about in the rest, yes, question?
Sorry, can I ask a short question?
Sure.
Yeah, earlier you showed you have large logarithms for the Newtonian potential. So if you get some over, do you get the good result at the end? I mean, it's clear for the other logs.
Well, I don't know. We haven't done it. We haven't actually done it for gravity yet. We're trying very hard. My friend Nick is actually visiting here for 3 weeks, and we're trying to solve just exactly that problem. There are a few little issues. One of them is, because of the shortness of time, I've truncated this talk. One of them is the fact that when you stochastically truncate to get an equation like this, if you take account of the fact that G tilde 00 is not constant, then this equation will not be a conserved part of the field equations. That kind of thing could not have happened in the nonlinear sigma models. It happens because of the gauge structure of general relativity. It's right, it's completely right, and you can see it happening in the lambda phi to the 4 calculation that I did. If you just take the leading logarithm term, you will miss conservation, so it will no longer be the case that rho dot is equal to minus 3h rho plus p. So it's right, that's right when you just keep the leading logarithm term, but it means that you have to figure out which of the 10 Einstein equations you take or which combinations you do. We have to figure that out. Fortunately, we have a lot of explicit results to compare against, so I think it's an eminently solvable problem, but we haven't done it yet.
Okay.
So contain your enthusiasm for a bit, and we will try and answer those questions, but there's some things we have to figure out first. So I hope I answered your question. In the remainder of the talk, I'd like to tell you about how to actually implement this. So remember, what we need to do is we need 3 coincident scalars, correlators. I call them A of t, B mu of t, and C mu nu of t. And those things are the things which tell us about the Starobinsky induced effective stress tensor. And we need them not just on de Sitter, which is easy, but we need them for a general homogeneous and isotropic background, which has undergone primordial inflation, and hence the name, hence the origin of the title, Remembrance of Things Past. I want to see how the late time result for these correlators remembers the fact that it underwent primordial inflation. And in that single field model that I told you about, where the effective potential takes this nice logarithmic form, the result that you would get if you had not just done it in de Sitter, but in a general background, would be minus 1/2 times the covariant scalar D'Alembert acting on A, where A is the bev of the coincident propagator. Okay? And once you have that, even if it's a complicated function, if you have that for this general A of t, even if it's a complicated function of A of t, it's just a one variable problem, right? It just depends on time, and you can evolve it numerically, even if you can't get it analytically. So it turns out these 2 extra correlators can all be gotten from A of t. For example, B mu is just gotten by differentiating A. C mu nu is a little bit more complicated. You get its trace by looking at 1/2 box A, and then the other component comes from the fact, it turns out there's only 2 components in a homogeneous and isotropic geometry. The other component comes from conservation of the scalar stress tensor. So everything comes from A is the bottom line. So let's learn how to get it for A. I want to develop analytic approximations, things written in terms of just scale factor, little a of t, under just the assumption that the thing underwent primordial inflation. So typically there are 3 epochs: inflation, where the slow roll parameter is between 0 and 1, reheating, and a hot big bang later on. A typical, to paraphrase Hawking, a brief history of time would be in terms of the slow roll parameter, and in terms not of co-moving time, but the number of e-foldings since the beginning of inflation. It might look like this. It's very, very small during inflation. Then it ends. The universe oscillates epsilon oscillates between 0 and 3 with increasing frequency, and then asymptotes to epsilon equals 2 in a radiation-dominated universe. Goes to matter-dominated, and then eventually has late-time acceleration. Okay? And that's the kind of geometry that we want to deal with. And the way that we're going to get the expectation value of the square of the field is we'll write it as a Fourier mode sum, a dimensionally regulated, because this is still divergent, Fourier mode sum in D dimensions of an amplitude script A of T and K. And the amplitude is the norm squared of the mode function. The mode function in D dimensions obeys the well-known equation with Wronskian equal to that. And it turns out that you can combine the equation and the Wronskian together to get a single equation for script A. And even if you were not doing what I was doing, it would still be better to use this equation because, of course, everybody who knows who's numerically simulated this thing, simulating the equation for U or the solution for U is a pain because U is complex. It has both a real part and an imaginary part. And in the end, for things like the power spectrum, you're not even interested in the imaginary part. So it's a real pain doing double duty. And it's actually better to have just an equation for the norm squared. And there it is. And the initial condition, even though you can't solve that for a general scale factor, the initial condition comes from the ultraviolet behavior, which is given by that. And what our technique is to take the full mode sum and, of course, integrate out the angular factors, again, in D dimensions, and notice that it's cut off with the modes which are super horizon at the beginning of inflation. Those would not have been amplified, so we're just setting those to 0. And then during inflation, we rewrite that as a part which is in the ultraviolet that has still not undergone first horizon crossing, plus a part which has undergone first horizon crossing. After inflation, we break it up into 3 parts: an ultraviolet part, a part which has undergone first horizon crossing and second crossing, and then a part which has undergone only first, which is still only first crossing. And very important functions are T1 and T2. So T2 is if something undergoes first horizon crossing at time T, then its second horizon crossing will be T2 of T. And T1 is that if it undergoes second horizon crossing at T, its first horizon crossing time would be T1. Okay, so let's go on. And here's the ultraviolet expansion. That's actually trivial, comes from the equation. It could be carried out to very, very high order. We've got it even at 6th order, but it turns out the only parts you need for wonderfully good accuracy, and you can see it numerically right here, is the first 2 terms, and that's all you need in order to completely capture the ultraviolet divergence. The form after first horizon crossing has also been known for decades before some of the people listening to this were even born. Its script A goes to h squared at horizon crossing times a complicated function, which includes all first slow roll effects over 2k to the 3rd. And if you wanted to, I actually have the form that includes non-local stuff that would involve derivatives of epsilon before horizon crossing, but that's typically so small that I don't even bother with it. And you can see that numerically on our synthetic geometry, so once you have a geometry, you can of course evolve these things numerically, and it's beautifully agreement. Okay, so yellow is the exact numerical result. Blue is the ultraviolet expansion. This is for something which underwent horizon crossing, first horizon crossing at n equals 10 e-foldings after the beginning of inflation. You can see that the ultraviolet form is just in perfect agreement right up until the moment of first horizon crossing. And then after that, almost instantaneously, the green form, which is the first horizon crossing form, is accurate. And like I say, we could improve this if we had to, but I don't think we have to. The form after second horizon crossing, of course, the thing then begins undergoing oscillations. It starts out with the amplitude of the first horizon crossing form. It's got a 1 over a squared term in it, and then because it's a mode squared, it goes like cosine squared of an integral that looks like that. And here's again a numerical comparison. Yellow is the analytic form given here, and blue is the exact numerical form. You can see that it's wonderfully good over here. A little bit of a problem at the beginning because this is the WKB approximation, and you all know that that goes bad right when the frequency passes through 0. But you could improve that if you wanted to. I don't even think it's important to do it. This is still got got ultraviolet divergences in it, and you use dimensional regularization to get those. So if you just take the k to the d minus 2 from the measure factor times the mode function, or times the expansion of the amplitude, you get a term like that, a term like that. And then you can do these things in dimensional regularization. It's in fact easy to do it. This one gives k to the d minus 2. That one gives k to the d minus 4 over d minus 4. Remember, the wacky rules of dimensional regularization are that whenever you have infinity, as you do here, raised to a d-dependent power, you always assume that that power is such that the result converges. So the upper limits don't matter. It's all coming from the lower limits, and there's the result. And by the way, for those of you who are math people, you can see that this d minus 2 epsilon times h squared is exactly the Ricci scalar in d dimensions. So that's neat. And then in the rest, what you do is to just set d equals 4, and you convert the integration over k to an integration over time just by taking the derivative, the differential of that, and you even keep the 1 minus epsilon term that we usually throw away, because, of course, you're doing this even to the end of inflation when epsilon would not necessarily be small. And I won't keep you in suspense. The result that you get for A of t, that's the scalar, the expectation value of the square of the field, takes this form. It's an ultraviolet divergent piece plus an integral over first horizon crossing times of an extra h from the measure and an extra 1 minus epsilon from the measure, and then times the first horizon crossing form. And the first term I'll call A divergent. This is the form that applies during inflation. After inflation, you still get A divergence plus some terms that come from incomplete cancellations of divergent pieces. And then you get two integrals here, and I've taken that cosine squared and just approximated it by a half. And that's the result that you get. And notice that I'm doing an integration over second horizon crossing time t prime, but it depends upon stuff that experienced first horizon crossing at time t1. And that again is the title, Remembrance of Things Past. So here you see it explicitly, remembering past physics. And by the way, let's compare this with what it would have been if it had just been exactly radiation dominated for all time. Then A would just be 0. Okay, so this is remembering the inflationary period, and it's transferring the huge scales of primordial inflation to arbitrarily late times. And that brings me to the end of the talk. So let me just give you my conclusions. And by the way, here, once I have A, that is the expectation value of the square of the field, I can then numerically evolve the classical fields in my nonlinear sigma models. And here's the result of a dimensionless classical field in the two field models. So during inflation, inflation ends between 50 and 60 U-foldings. And during inflation, it grows and grows and grows, and then it falls off somewhat after the end of inflation, but it's still quite significant today. And if I had made it, I could have had it live an arbitrarily long period of time, and then it would have gotten quite big. Okay, so what are my conclusions? First off, graviton loops on de Sitter give factors of logarithm of A and also sometimes factors of logarithm of HR if you look at exchange potentials like the Newtonian potential or the Coulomb potential. We finally, after so long of struggling around, have a way of summing these things up and also propagating them to arbitrarily late times. And as an example, suppose we take those forms that I give right here and we apply that to radiation domination. So H of T prime falls off like 1 over 2 T prime. A grows, or A squared grows like T prime. So this is a wash. This is a constant. And that means that this term is basically growing like T, but it's multiplied by something that's falling off like T. So this is a constant times the big scales during inflation. This term over here is falling off like 1 over 2 T. but that means it grows logarithmically in T prime, and it's not multiplied by anything that falls off. So in fact, that's going like logarithm of T. And that means that even after you take two derivatives of it, what you get is something that looks like the local h squared of T times an h squared during inflation. So it remembered that the universe had undergone a period of primordial inflation, and it propagates the huge scales of primordial inflation to arbitrarily late times. I think that's a hugely significant result, and that's the explanation for my title. Lessons of this to building non-local models of cosmology. Well, the thing that makes everything work, box of A finite, is some non-local scalar, because A is the expectation value of a scalar, and box is a scalar differential operator. So it's some non-local scalar, but I'll be damned if I can recognize it. I've been building non-local models of cosmology for decades, and it's nothing I would have guessed. The thing that makes it so hard is that it's not just this part, which is an integral, but it's also this part, which depends upon the time of first horizon crossing of something that experienced second horizon crossing at T prime. There's no simple differential operator that gives that. So it's a very complicated non-local scalar, but that's what theory says you're getting. And the form that I've got already is enough to build non-local models of cosmology. It's not enough to figure out what happens to the gravitational force, because we need a more general geometry. We need to know what it is for more general geometry. So I would love to be able to recognize box of A finite as a non-local scalar, but I haven't done that yet. Anyway, that's the end of my talk. So I will stop here and entertain questions.
Thanks very much, Richard. So we got time for some questions. If people want to, well, raise their hand in Zoom fashion or jump in there. Yeah. Maybe Shravan, you have a question?
Hi, Richard. Somewhere in the middle of your talk, you're speaking about S matrix. I'm just confused. You're speaking about S matrix in de Sitter?
Well, I don't think there is an S matrix in cosmology. What I meant is that as somebody asked, I think it was you actually, well, somebody asked, maybe it was Alexei, asked the single field model. Let me get back up the Lagrangian of the single field model. Let's see right here. So can everybody see the Lagrangian of the single field model right here in red, first red line? Yeah. So every single field nonlinear sigma model is reducible by a field redefinition to a free theory, and that's indeed true. And there's a theorem due to Bohers that says that if you can reduce something to, well, it says that any two theories which are related by a local invertible field redefinition, which this and the free version of this are, have exactly the same S matrix. The S matrix is not changed by a local invertible field redefinition. So in fact, this theory on flat space, where it does have an S matrix, would just be trivial. It would have a unit S matrix, and people who were S matrix fanatics, people who believe that you can get everything that you might want to know, all of physics, Coulomb potential, everything could come from S matrices. Those people would just dismiss this theory and say, gosh, it's not even interesting. They're wrong. The reason they're wrong is that, first off, an S matrix doesn't even exist in general in cosmology, and even if it did exist, it wouldn't be observable. Secondly, there are things that the S matrix doesn't tell you. For example, this thing has an interesting background field evolution. I showed it to you. In fact, I explicitly solved for it. And I didn't tell you, but the one particle kinematics also has interesting behavior. This thing will develop masses, time-dependent masses, and I think that's interesting to follow. So this is an explicit counterexample to those people who are what we might call S matrix chauvinists, people who believe that S matrix is just everything, it's the end all and be all, and that's just not true. And here's an explicit counterexample, and there are a lot of them.
Okay, thank you.
Thanks. I was really nice review you went through at the start of the different applications and sort of identifications of the stochastic behavior in different models. I think the scalar models you've talked about, am I right in saying they're all spectator models in the sense that you're solving on the fixed background? And
that's right.
And I was just wondering, of course, those of us doing calculations in inflation often are interested in the inflaton, which is coupled at least, albeit weakly through the slow roll parameters to the metric.
Right.
Where does how far can you get, including the self-gravity of the fields, basically?
Well, that's really something that Alexei and I guess Andre Linde have worked on much more than I have. But the answer is that you can go ahead and apply, as long as there aren't any derivative interactions of the scalar, you can apply this formalism to even the case where it's the inflaton. And then you would have to change the free field mode sum a little bit, because as the geometry changed, the free field mode sum would change a little bit, but in a controllable way, a way that you know. And you could, I think, in principle, do that. And Andre Linde has thought about that quite a bit. He's typically interested in big jumps of the scalar field rather than the sort of small cumulative jumps that I'm talking about. But I think the formalism applies.
Yeah.
And I think there's an industry of people who do it. Yeah.
I mean, there's actually interest. I think currently people are beginning to play around with stochastic tensor or trying to develop, apply, I think, the stochastic formalism to the tensor fluctuations, gravitational wave distribution.
Now that's something that you would need this formalism for, because see, that's where you have derivative interactions, and there you would need to use the techniques that I told you about in today's talk.
Yeah. So I think, that would be interesting.
And the literature on this is a little bit peculiar. Many people just try and apply the scalar potential formalism to gravity. You can see by explicit calculations that that doesn't quite work. And there's a good reason why it doesn't work. It shouldn't. You can see exactly where it fails in the proof, and because also there's this extra source of large logarithms that can occur from the ultraviolet that wouldn't occur in scalar potential models. So it's trying to use the formalism for something that it was never designed to do. But what I've told you about today is that there's a way of extending it so that you can, in fact, use it, plus the renormalization group that, of course, we know how to sum up to get everything.
Yeah, I think that would be very interesting. Yeah. Okay, I think.
Up at night.
Thanks very much, Richard. It's a very interesting talk. I guess we should move on. I think Andre is there. Yes, I can see you, Andre. Welcome. Good morning to you.
Good morning.
Good morning.
And
great that you made it so early to joining us.
Great, and we can see your slides now. So it's a pleasure to welcome Andre Linde from in California, yes, in Stanford.
Yeah. If you see that I am asleep, that just explains many things. Okay.
Please go ahead.
Okay. So today I will discuss hybrid cosmological attractors and PBH formation in early universe. And it's, of course, the subject which David Vance is very familiar with, because that's how we started a long time ago. The plan would be first to remind our old paper by Garcia Belida, Lance, and me about hybrid inflation and primarily black holes, see what should be added to it, perhaps suggest some methods to do it, and then these methods would involve cosmological attractors. So we will discuss the model which will just achieves this. And this was a recent work with Braglia, Kalush, Finelli. Okay, so let's start. First, this is the paper which I mentioned already. So what
Andrei, just to
Yeah.
interrupt, but you're not quite in the full screen presenter mode. I mean, we can see it clearly, but if you wanted
okay.
to click on,
Okay.
yeah, that's it. That'll
How
be
about that? Mhm.
okay.
Good.
Yeah, that's fine. In
Thank
fact,
you so
very
much.
similar. Thank you.
Yeah, I knew that you will stop me if I do something wrong. Okay, so first, this is just abstract of our paper, and what we were trying to say that sometimes in hybrid inflation we're able to produce fluctuations which can be huge and have some peaks, and these peaks can be useful for production of black holes. And we were even bold enough to suggest that these black holes might even be responsible for dark matter in the universe. So it is a long, long time ago, and I am revisiting it now. So basically, what we have in the beginning is a model of hybrid inflation, which I'm reminding you now. This model has a very simple potential of two fields, though. One direction, one field is phi, and you may take in the beginning just a simple potential, which is quadratic. Then there is another potential, which is field chi, whatever you call it. Different people call it different names. This is essentially Higgs potential. So you have a potential which has a maximum at chi equal to 0 and a minimum at chi equal to chi 0, whatever chi 0 is. And then there is an interaction between these two fields, a simple term phi squared, chi squared, okay? So now typical potential looks like it is shown in the picture. So you have at very large values of the field phi, which will in the beginning play the role of the inflaton field. You have just quadratic potential, and this term disappears, the last term, because at very large values of the field phi, this last term, which disappears in the potential, last term makes the field chi very heavy, very massive, and therefore minimum with respect to field chi at large phi is at chi equal to 0. Then when field phi rolls down along the valley, along which it has simple potential m squared phi squared, then it comes to some point where the first term becomes important, because we know that the first term, Higgs term, has a minimum at chi equal to chi 0. So at some particular point, which we'll call phi c, critical field phi, which is equal to m divided by constant g. At this point, this direction with respect to generation of the field chi becomes tachyonic, and field chi falls down either to the right or to the left, and inflation may end. So there will be two different possibilities. First, the comment for chi equal to 0, it is chi equal to 0. It is just quadratic potential, and however, this quadratic potential is uplifted. Some additional term is added to it, which means that this Higgs potential uplifted slightly up. Okay. Now, if chi much smaller than 1 in Planckian units, then at the critical point, which is m divided by g, this critical point, rapid waterfall appears, and the scalar field chi falls down to its true minimum pretty quickly. However, and this is the regime which we will mostly concentrate in this talk, this is a different regime, which is not what originally was looked for in hybrid inflation. What if this chi 0 is larger than 1, or of the order of 1 in Planckian units, or just a little bit smaller than 1? In this case, sometimes this fall down of the scalar field by itself creates inflation, a second inflationary stage here. So this is the inflationary stage which will be interesting for us. And to get some intuition what is going on here, because this is complicated. You have two fields, they are fluctuating simultaneously, they are moving simultaneously, but to get intuition, it's very helpful to focus just at this Higgs potential, which is this hybrid inflation at phi equal to 0. So Higgs potential at phi equal to 0 is shown, and what I will explicitly show at the next page, if chi is greater than 1, then it is an inflationary Higgs potential. So if you start at chi equal to 0, you do not immediately fall down, but instead you fall down very, very slowly. And not only very slowly you fall down, but also you can fall down to the right or to the left. And there are some points where field phi will stay equal to 0. And so you'll have eternal inflation. And this eternal inflation also produce eternal inflating topological defect, something which with Vilenkin studied a long time ago. So it is a pretty complicated picture, but sometimes it's possible to make it slightly less complicated, and that's what will be my main effort today. But also a comment, even though we will see that eternal inflation in Higgs potential exists only if chi is 0 greater or over 1, then in Higgs, in hybrid inflation, everything is trickier, because when I am coming to the critical point, at this time, in the beginning, the potential is not tachyonic, then it gradually becomes tachyonic, and it must become a real full Higgs mass only at the very end. So there will be some interesting dynamics in the between, and that was the main subject of study in our paper with Linde and Vance long time ago. But once again, about this intuition for the simple Higgs potential, because it's very simple, it's not always widely known, so let's consider it. You start with Higgs potential, and you just calculate all the properties of this potential at chi equal to 0 at the top. So the first derivative obviously is 0. You have some non-zero uplift, and the second derivative is minus m squared. So you have tachyonic mass m squared. And then if I compare the second derivative with respect to field chi, when the field phi is running, it is already smaller than the critical value. Field already wants to fall down. Field chi already wants to fall down. Nevertheless, this tachyonic mass is smaller in absolute magnitude than the tachyonic mass in the end of the way, where scalar field becomes equal to scalar field phi becomes equal to 0. So the lesson is this: if for whatever reason there is an eternal inflation at point phi equal to 0, then it's even more so on the way towards this point, because the second derivative all the way up to the point when phi becomes equal to 0 is even smaller. And the second derivative divided by v is equal to 4 divided by chi 0 squared. So the inflationary conditions, slow roll conditions are satisfied, because at the top of v chi, so first derivative with respect to chi is equal to 0, and second derivative, if chi 0 is greater than 2, then you have another slow roll condition satisfied, so you have inflation. And moreover, it is possible to show that this is eternal inflation in this regime. So essentially, if you have new inflation, it's always eternal inflation, especially clearly was shown in the paper by Vilenkin. Okay, so now if you consider what is the magnitude of fluctuations produced at that time, then it's given by this equation. And at top, this equation gives you just formally infinity. But of course, you are not always exactly at top, because scale of fluctuations move you slightly to the right and to the left of it. So the lesson is that if you start close to the top, then amplitude of the fluctuations is extremely large, of the order of 1. And of the order of 1 fluctuation is exactly what eternal inflation tells you about, because it can just start inflating, and then some parts of the universe jumps up again the floor, and then they flow again. So there will be always parts of the universe where eternal inflation continues, and there are always part of the universe where inflation is over. And this would mean that the amplitude of fluctuations is large. So basically, this means that if the condition chi greater than Planckian mass, chi 0, is satisfied, then it is very, very natural to have extreme fluctuations of scalar field, extreme fluctuations of density, and therefore it is very natural to expect that black holes can be produced in the process. That's what was established in our paper by Garcia-Belida and once, long time ago. And of course, the investigation was much more technical than what I just said, because we were studying different fluctuations in different regimes, calculated what could be the amplitude of resulting fluctuations of density using delta n formalism, whatever. So we found that black holes can be produced here. And as I just said, this is two-field evolution. So in reality, we must do it more carefully. But also in reality, in '96, when we studied it, nobody cared. Well, people cared, but they are not worried by the fact that in this simple hybrid inflation scenario, NS is greater than 1. So nowadays, this theory is well ruled out. So then why do we need to even study it? And well, I hope it will be clear later. But there are many different ways to modify the potential to avoid it. And of course, this is a rather famous paper by Klesse and Belida, which, in my opinion, restarted the interest of PBH production in the early universe in a substantial way. And they modified the potential. So they have, except for instead of letter chi, sigma, they use letter psi. This is this is hybrid inflation potential, but instead of simple term m squared phi squared, they added a combination of a linear and quadratic term. And what is important is that a quadratic term was taken with a negative sign. Why did they need to take it with negative sign? Exactly because of this NS. NS is approximately equal to 1 plus some coefficient, and this coefficient is positive for normal mass squared, and accordingly negative if you change the field mass and it becomes tachyonic. So they studied this model, and if you exactly put the initial conditions to exactly proper place for this model to start working, then it actually may work. Unfortunately, that's the problem, because if you plot the potential for this model, you will see, not unexpectedly, that if you start with a theory which has tachyonic potential, then for the main range of initial conditions, instead of realizing inflation, just hybrid inflation, you just have a global instability when the scalar field, because of the tachyonic instability, start rolling down, and then the universe after that quickly collapses. So if you take initial conditions initially that the fields originally are large, then typically it ends up with almost instant instability and therefore no hybrid inflation at all. And if we study different initial conditions, like some with the small values of the scalar field phi initially, and study just trajectories in the space of two fields. So if the field phi is small, then you have this field falling down pretty quickly, and hybrid inflation is not realized. And if you start with a large field phi, then the worst thing happens. The scale fields start oscillating and then start moving to large field phi, and the universe collapses. It is always possible to find the set of trajectories which realize the scenario, but it has measure 0. Okay, now, recently there was a suggestion of further modification of that. So if 2 terms are not enough, then let's add the 3rd term. And if you are just following this strategy, you may produce proper NS and everything is good, except for when you modify it at the cubic potential, then the global structure of the potential becomes very different. And in particular, if you use the numbers which they give as an example in their paper, then there is no even minimum at v equal to 0. And the authors know it. They just said, but we were interested only in study of what happens in the vicinity of turning points, stuff like that, which is a very, very good to know these details, but you need to have a global picture unless you can do it, so nothing works. So it's possible to add the 4th order term. Okay, so nothing is impossible, but it would be nice to do something different and maybe simpler. And that is why we turned back to alpha attractor models as a possibility to realize this, because in alpha attractors, it's very simple to implement the conditions which give results for NS consistent with Planck results. There is additional problem with this set of models, which we mentioned already in our paper with Linde and Vance, and that is these models, just to make them simple, they had a simple Higgs inflation, simple Higgs potential, which was symmetric with respect to the change from chi to minus chi. And if we study these kind of models, then they have domain walls. And if you have domain walls with the amplitude of the symmetry breaking, which is Planckian, then these kind of models, they are just definitely ruled out. It's possible. It's not just the question of inflation, it's just horrible cosmology. So we discussed it, and it is possible to overcome these difficulties in several different ways. And one of these ways we realized in our paper with Braglia, but that is not the only way. I will discuss it later. Okay, but first, some quick reminder, what are alpha attractors? Alpha attractors, you just take normal Einstein theory, take any kind of, almost any kind of scalar potential, and the only thing that you change with respect to standard theory, you take a kinetic term which have a singularity downstairs. And it would look dangerous to have the singularity, but as the previous speaker explained, it's always possible sometimes, not so always sometimes, it's sometimes possible to massage this problem out by just making field redefinition. And by making field redefinition, you reduce this theory to a theory with canonical kinetic term and unusual potential. The same potential is a function of hyperbolic tangent. So then the question is, what is the trick, why we're using it to start with? And there are 3 different motivations. First of all, when we studied the structure of Starobinsky model and Higgs inflation, in each of them, in Starobinsky, for example, you start with r plus r squared, but then you make some change of variables and change of everything. And then in the way, in the end, you get a potential which has a flat potential plateau. And on the way to it, in some intermediate calculations, you have this singular kinetic terms. You just make this transformation and you get potential in desirable form. The same thing we found is in Higgs inflation. And then we start working on it, and then we found that it is also these kind of terms, they have natural implementation in theory of supergravity, and they're related to hyperbolic geometry. So whatever is the reason, there is a very large class of models where potentials produce it in the similar method, they acquire flat parts. And one of the interesting properties of this potential is that at large values of the field phi, you can expand this potential, and it is just constant minus some exponent. And this exponent is universal. The next corrections are double exponents, so they are pretty fast decrease. And the coefficient in front of this exponent can be absorbed in the redefinition of the field phi. So in the end of the day, your observational data are determined only by V0, which is responsible partially for the amplitude of perturbations, and the alpha, which is responsible for the tensor to scalar ratio. So this model is highly predictive, almost independently, largely not dependently on the value of the potential phi, which is an interesting property. If we study a different set of models with also singularity here, then it is possible to follow the same logic, make the change of variables, and you have a potential which is generalization of the Stravinsky model. So Stravinsky model would correspond in this terminology to alpha equal 1, although it has completely different initial realization as a theory R plus R squared. And that's how the potentials look. So this was a quick introduction of what alpha attractors are, and this is the experimental status. So if we look at the relatively recent paper by Bicep, and they summarize it and the picture results of Bicep and Planck all together, you will not find in the paper these curves. This is something which we just added. So what you will find that all theories m squared, phi squared, or phi to the degree 2/3, all of these theories, they are ruled out by a combination of Bicep and Planck. But alpha attractors, they just perfectly come to this interesting blue area, and they're essentially saving monomial potentials, because if you start with any theory like V of phi equal to, say, phi cube, then when you introduce this alpha, at small alpha, predictions of the theory all zoom towards this blue ellipse of Bicep and Planck. So it is pretty suggestive that maybe there is something interesting in this class of theories, especially if they match Planck data so well, at least potentially, slightly depending on the choice of the original potential. But at small alpha, this dependence gradually disappears. Okay, so this is one thing. And that's something else which appears if you study realization of this theory in supergravity, and it goes back to some paper by Ferrara and Kalash many years ago. They have found that this parameter alpha has several preferable discrete number values. It is like start from alpha equal to 1/3, and then 2/3, 3/3, etc., up to 7/3. So there is a ladder of possible values of alpha which are preferred in supergravity, and in the E models, which are like generalization of Stravinsky model with different alpha, the ladder looks slightly different, slightly shifted to the right, but also it has the same set of parameters alpha up to 7/3. And if we look at this Bicep Keck data, and you will check this prediction of the upper part of this ladder corresponding to alpha equal to 7/3, interestingly, the corresponding part of the ladder just crosses this blue area, which is preferred by Bicep and Keck, which does not mean, of course, that their data confirm already this alpha equal to 7/3 model, but it's a pretty interesting coincidence. Their results are not sufficient, the accuracy is not sufficient to make any such conclusion, but what they hope at least they hope that this accuracy will be reduced. It will be 3 times better within several years from now. Let's hope that it actually works, or we'll wait for some other experiment. What I wanted to say that already now, not somewhere in the future, but already now, experimental data coming very, very close to interesting cosmological models, which may be well explained. We will see what happens in the next few years, because maybe we will not find anything in this region at all. But we are in the area which can be tested pretty soon. And the quick excursus to LightBird. When they study what they are going to find, they plot this possible data, and maybe on the left one, you will see here this ladder of 7 different predictions of alpha attractors going from extended supergravity. And there are some lines for Starobinsky model, for Higgs inflation. So you have some targets. But what is interesting, that the right hand of this blue area, which right part of the blue area, which is preferred by them, is not occupied by any theories which would be interesting enough for them to add them to the graph. And this is kind of dangerous, because this already means that from the very beginning, if you start with that, then you have 50-50 chance that maybe reality is out of our theoretical description. And so it is possible actually to extend predictions of a model to the right-hand side. And it is possible to do it in general formalism when you have general pole inflation. Previously, when you have non-minimal kinetic terms with a coefficient with parameter q here equal to 2, that generated alpha attractors like this model. This would correspond to this E models generalized at Starobinsky. But if Q is greater than 2, then these models produced in a similar way, they actually have a polynomial type of structure. And this polynomial type of structure appears not only in this pole inflation, but also in brane inflation. There are several different ways to come to the models with potential of this structure, including this, as I said, pole inflation. So you may have potential which looks like phi to the 4th divided by f2. So they look like something which also reach plateau, but reach plateau not exponentially fast, but polynomially fast. And if we plot predictions for experiment using these models, then we will see that here this yellow T alpha attractor model, red alpha attractor E model, and all the rest are other models which either follow from DP brane inflation or from pole inflation. And it is also possible even to obtain them from alpha attractors if you reduce one of the standard requirements which we previously used. When we study V, we have chosen V to be non-singular, and we also assume that its derivatives to be non-singular. But if we instead allow derivatives to be singular, then we also obtain this set of models. So for us, it is just a reason to look at this polynomial type of model seriously. There are several different reasons to bring us to us, this model to us. So we'll also study these kind of attractor models. And why I'm calling them attractors, because again, they make predictions which in terms of NS, in the limit of small parameter mu, they are not sensitive to the value of mu. And instead of R, they predict R, which decreases and decreases when the mu is decreasing, and it can take any possible value. So this, we call them polynomial attractors. If we study all of these models, then they can predict NS starting from 1 minus 2 divided by n to 1 minus 1 divided by n, which is pretty broad range. They cover all the range in which LightBird is looking for for explanation of possible data which they might get in the future. And the same thing is valid for CMB-S4. So it is possible to cover this blue range of interest with this set of models. Now, but the situation can be, in fact, worse than that. And so what will happen if we will have the trouble to kind of make peace between H0 model, between the supernova and CMB, and sometimes people start studying early dark energy, new early dark energy, etc. And in some of these models, the authors required reinterpretation of existing data, and this reinterpretation pulled the interpretation to NS even close to 1. So can we be even more flexible? And this was a substantial surprise for us, because alpha attractors are pretty predictive. They predict whatever they predict. However, if I take two field alpha attractor, and for simplicity, this is just, well, hybrid inflation, which we discussed previously. So in this set of models, you have an interesting feature. If we do not have alpha attractors yet, just this is a standard hybrid inflation. And then I study NS in this set of models. And then NS there depends on the uplift of the potential which I have. Just normal potential, for example, is m squared phi squared, but it is uplifted when sigma or chi, whatever field here is, when you are at the reach of the potential, this quadratic potential is uplifted by term m to the fourth divided by 4 lambda. Okay, so this uplifting make a change. If you look at the value of NS appearing here, and you start looking at V prime, which appears from m squared phi squared, and you look at V, V has this contribution of uplifting. If I increase and increase uplifting, the last two terms, they just disappear. V prime and V2 prime do not depend on the uplifting, do not depend on this term, which is first here, m to the fourth divided by lambda. But V does depend. So at the limit of large V, these two terms disappear, and you have a limit to NS equal to 1. And now, interestingly, if we study the same thing in hybrid inflation, where instead of normal scalar fields, I introduce both of them will make alpha attractors. So both of them having poles. Then alpha attractors in the large N, large number of foldings, they nevertheless, they do have this alpha attractor prediction. So everything remains correct. However, the question is whether N of the order of 60 is already large enough for this attractor to be realized. And what happens here is that if I increase uplifting, then the range of changes of the scalar field phi with the increase of uplifting becomes gradually shrinking. So previously it was pretty large, determined by the theory of alpha attractors, but if I uplift it further, then the speed of motion of the scalar field phi to its minimum at phi equal to 0, the speed of motion decreases during the same number of folding. You cover less range of scalar field space, and then you go to the range where the potential is in fact effectively canonical. And in canonical model, as we just discussed, in canonical hybrid inflation, you have a prediction NS equal 1. So what we have here is a strange situation that depending on the strength of uplifting term, which is in our hands, this is just a model. So if the uplifting terms is not too large, then your predictions are the same as in normal theory of alpha attractors. But if I continue rising and rising uplifting, then the prediction match the standard hybrid attractor model. So we have a flexibility. If somebody will tell you that we need a theory which explains very large NS, then starting from alpha attractors, you may cover all the range of NS from this 1 minus 2 divided by n to NS equal to 1. Even more than that, but that is a special discussion. Okay, so whether it is a good result or whether it is not a good result, if you want to get this result in the theory of alpha attractors, you need to make the theory more complicated. Two fields, a larger plea. So it does not come naturally. Natural prediction of alpha attractors is what previously it was. But I can massage the theory into predicting many different things if needed. And now, finally, what happens if we study this theory and look at the potential? The potential, if you have a critical value of the field not too large, then the theory behaves just like it was behaving before, qualitatively. But if you study alpha attractors with value alpha, which is rather small, then what you will see that when you are trying to plot the potential at large values of the field phi, you will see that large values of the field phi are already beyond the singularity. And therefore, in this kind of theory, even at infinite value of canonically normalized scale field phi, you always have spontaneous symmetry breaking, and therefore you never produce any topological defects. And then there is another regime which is also possible here. If you have sufficiently small parameter lambda there, which means that value of spontaneous symmetry breaking in your potential is large beyond the limit where you have this singularity, then the potential never has a minimum. So the scalar field continue rolling down, and this potential is exponential. And this means that you have a quintessential inflation or dark energy within the same model. But we will not discuss here these models without topological defects and quintessential inflation. Instead of that, we concentrate on a slightly simplified version of this model with just one of the fields, field phi, inflaton field, being attractor, and chi we will keep for simplicity normal canonical field. It is already sufficient to get what we want. And potential looks the way we wanted it to look, so it is a standard hybrid inflation, almost standard hybrid inflation intuition, except for at very large values of the field phi, the potential becomes flat because it is tangent instead of phi squared. If we study evolution of the fields starting from the large values of the fields phi and chi, then the final results do not depend on these values. So this is a very nice property of stability of whatever happens with the theory in the end with respect to the choice of initial conditions. One thing which I did not mention, but I will show it to you. This is an additional term which we added here, the last term in the potential, which is linear term with respect to chi. So this is a term which produces tiny violation of symmetry chi to minus chi. So it slightly changes the symmetry of the potential. It is so small, this term, that it is not even shown here. At this picture, everything looks symmetric. But if you study how the evolution of the field works, then this tiny term becomes important. And here is the reason. So if we start studying again, as we did before, new inflation in the theory, in the Higgs potential, and just add the tiny term d. Now, everything will be as before with respect to curvature and with respect to initial value of the field of the potential, but there will be tiny linear term appearing here at chi equal to 0, and this linear term will be important because at the top of the Higgs potential, instead of putting v of chi equal to 0 in the denominator, which would give rise to huge perturbations of density, instead of that, you will put there this m squared d chi. squared in the denominator. So it will be finite. So it will be normalized by the coefficient d. And it is sufficient to take this d very small, like 6 orders of magnitude smaller than other parameters of the model to achieve the desirable goal. So it is possible that even at the top of the potential, your amplitude of fluctuations becomes smaller than 1. How smaller than 1? Depending on the choice of this additional term d. So by choosing this additional term d, we can normalize the height of the peak which appears here. So instead of eternal inflation, you have inflation which produce very large fluctuations, normalize it, or making a cut by the presence of this linear term. And this is, again, just an intuitive picture. To study what really happens there, you really need to study two-field evolution. And that is what was also done in this paper. Thanks for our powerful collaborators, Braglia and Finelli. And what happened is something which we could predict, but it is nice that this prediction really appears to be correct. So if we take d like 10 to the minus 6, this will be the amplitude of the peak produced here. So this peak appears in the range of n, which is, well, close to the end of inflation, but the position of the peak, in fact, depend on d and on other factors. And depending on d, you can make this peak very high or lower than that. Then we can change another parameter, chi0, which is amplitude of spontaneous symmetry breaking. Again, if you take this chi in this particular model of the order of 2.5 in Planckian units, then this will be blue line prediction. If we start decreasing it, then the top of the peak moves to the shorter wavelengths. So this means that if we want to produce black holes here, for example, then we have a tool of controlling the amplitude of the fluctuations here and also the position of the peak. If we want to get smaller black holes, it's easy. You just change chi0 and you get the smaller black holes. And then there is another parameter, how narrow this peak is. And the narrowness of this peak, not the position of the maximum, also can be controlled, in particular by changing a coupling between this Higgs field and the inflaton field phi. So when we have a large coupling, then the peak becomes more narrow. And the meaning of this is the following. If you look at the left part of this picture, this left part of the picture is mostly the fluctuations there are due to enhancement of and conversion of previously produced isocurvature fluctuations to adiabatic. So when the field was just rolling down, the scale field was rolling down the potential, coming closer to the point, to the critical point, already at this time, the curvature of the potential in the direction chi becomes relatively small, and you start producing fluctuations of this field chi. And then when you just start producing them, they are either curvature fluctuations. But later, when the field chi start moving down, then these fluctuations will be converted into adiabatic perturbations. So this part appears, this left part of the maximum appears before the field even reach the critical point, okay, due to this, what happens at this time. And the existence or non-existence of this contribution depends on the value of on the strength of interaction between field phi and field chi, because if this strength of interaction large, then the curvature of the potential before it reach critical value is very large, and these fluctuations are suppressed. So there are many different ways to play with the shape of the maximum which we produced. And because we had this breaking of symmetry between chi to minus chi by this term d, not only we normalize the amplitude of fluctuations so that it is smaller than 1. But this normalization is because when we follow the trajectory of the fields phi and chi to the minimum, this trajectory always is off from the ridge where the field chi would have a choice to fall to the right or to fall to the left. So there will be no topological defects produced in the theory. Whether you like this solution or not, it is a different issue. There is no principle which would forbid violation of discrete symmetry in this model. In fact, people who study quantum gravity, every week they publish papers saying that discrete symmetries are always broken. Okay, so if we break it at the level 10 to the minus 6, it is already sufficient. And these curves, which I'm showing right now, they are obtained in the power law models, which I mentioned to you in the second part of the talk. So it's not necessary to consider models with Stanch potentials. Instead of them, you can have this KKLT type of potentials, and you still get desirable results. And this graph here shows what is the NS which we are obtained at the CMB range. So it is quite possible to satisfy Planck data if we want to do it. And as you see here, also by choosing parameters, you change the position of the maximum and the width of the potential. So I'm basically finishing. This is the last slide. And first of all, I should mention that hybrid inflation had many different stages of its evolution. Originally, it was just simple phenomenological model. Then later, people start introducing it in supergravity, and the models radically changed. But in the case which was for quite a while rather popular, this structure of potential strongly depended on quantum fluctuations. Here, the scenario which we described with these potentials, it appears already at the classical level, and it is in our papers, it is implemented in supergravity. So it's full-fledged supergravity theory if you are interested and do it in supergravity, or you can consider it as a phenomenology if you do not want to go into details of supergravity construction. Is it possible to avoid adding these linear terms? Because some people do not like it, and I would prefer to avoid them as well. And it is always possible to do something, but for everything that you want to do, you have an entry price to pay. It may be possible. We are planning in principle to study it, but it will be a different kind of calculation. Just to get an idea, if you have just standard, very old new inflation scenario, where you have just SU5 model, you couple this SU5 model with scalar field phi, which is inflaton, which will be hybrid attractor. I'm sorry, just alpha attractor. So you have effectively hybrid inflation with a new inflation at the last stage of it. And the new inflation will make short, because the shortness of it depends on the quality of the inflationary potential of the model. So you can do this, and then in that model, you have a short stage of new inflation, produce it, unfortunately, at that time, but fortunately now, producing large fluctuations of density. So we can have large fluctuations responsible for black holes, and we have hybrid inflation. And in this case, SU5, instead of having terrible domain walls, you just have super heavy monopoles. But we'll have super heavy monopoles, and you have also super heavy black holes. But because super heavy black holes are much heavier than monopoles, then monopoles will play no role in the cosmological evolution. So I'm just dreaming right now, but I'm just trying to show that the general principle which we used from our paper starting from 96. It can be realized in a large set of different models, and this is just one of the realization. And the last thing which I should mention, and well, especially our co-authors will like it more, that in addition to producing black holes, which is a complicated story, there is an addition, you may produce stochastic gravitational wave background, which will be a target of other set of future experiments. Okay, so that's it. Thank you very much for your attention.
Thanks very much, Andrei. Fascinating talk, of course. And we have time for questions, I think, and indeed we'll go into a discussion at this point. So if people have questions, please raise their hands. I can see Alex has already. Alex.
Hi, Andrei. It's great to see you. And I have a very actually naive question. So if we increase by such an amount the amplitude of quantum fluctuations and inflation on relatively short scales, but not extremely short scales, maybe, wouldn't it mean that we also increase non-Gaussianity? Or may increase non-Gaussianity?
The question is, at which scale will you increase non-Gaussianity? So what we studied, it's not just even non-Gaussianity, because on the way towards this point, as I mentioned, you generate controllable iso-curvature fluctuations, which later convert into it. The very fact that you produce later black holes, it means already non-Gaussianity, all right. The issue is that at least at this naive interpretation level, which we have right now, you produce all of these at a very short, controllably short range of waves. So these words controllably, I emphasize all the time, because what we see that you introduce several different parameters and you have a general principle. Do this and you get what you want or do not want. Okay, so it seems that at least naively, without theorems stating otherwise, everything works the way we did, and the spectrum of fluctuations was studied. It was studied by methods which by now are standard, so we did not find any pathology here except for small region. However, as all of us now know, that there is right now ongoing debate whether, for example, in the theory of one field, you have some problems producing black holes because once you get something large in the short range, it may convert back, affect you back at the long range. No such theorem is known for the two-field model like that. And even for one field model, if you read Riotto, he will tell you that it is only, this problem appears only if you have a rapid change from one regime to another. So I am not going to make any theorems at this time. I'm just saying that qualitatively what we see seem to work, and that's the maximum which I can say.
Thanks. That's very interesting. Thank you.
Okay, Sergey Vernov, we have a question.
I have a question about your alpha tactor models. If I understand, you have some up boundary for initial condition of your field phi. You need some fine-tuning of your initial conditions, right?
It is right and wrong simultaneously, as always with interesting questions, right? You see, because what we start with this construction, you have some fields living in hyperbolic space. In this hyperbolic space, you cannot go outside of the boundary of this hyperbolic space. So you may say, how is that? Well, your field cannot go beyond some value, what we are doing with infinity. Well, that's a property of hyperbolic space. If you go to canonical variables, then the corresponding canonical variables becomes infinite. So what I'm saying is that if you play the game in such a way that here is a theory, say, supergravity of a special type. In the theory, there is no fields which go beyond the boundary, the whole theory defined there. So no problems with initial conditions putting you to some small range. If you convert to equivalent theory, just different formulation, where this looks canonical, then your normal intuition, what is possible, what is not possible, returns to this model, and you see they can go to infinity, no problems with initial conditions. But maybe your question was about something else. Maybe it is in normal chaotic inflation, for example, you have theory m squared phi squared, and the field phi can rise up to Planckian density, and then Planckian density start with Planckian domain, so it is relatively simple to get the Planckian size of the universe relatively homogeneous. After that, the whole world becomes homogeneous. Here, if you go along tangent, you never reach this Planckian boundary. But, for example, in the simple model which we studied here, and that is maybe because we took it, I had one of the field, this field of phi is attractor, and its potential is tangent, and another field chi, and the field chi grows at large values of field chi up to infinity. So you start inflation with the field chi, and then the field chi falls down to the valley. This is what is shown here. Field chi falls down to the valley, then the field rolls down along the valley, and then you have everything else started. So if you want to solve the problem of initial conditions in the same way as chaotic inflation, you just do.
Yeah, my question, what can you show previous slide? Your initial condition of your field phi should be less than 6 alpha.
It not could be. It must be, because,
yes, it must be.
Because
for me it is what some fine-tuning for initial condition. What?
If you consider a theory which has phi greater than square root of 6 alpha and phi smaller than, but when you study from the theory which is a basis for this theory, is a theory of supergravity, you just formulate the theory on a disk, and there is no anything outside of the disk. It's called Poincare disk. So this is not a question which is intuitive or not intuitive. The theoretical construction is defined. It's just like a closed universe. How is that there is nothing beyond the closed universe? It is a very similar analogy. You have a Poincare disk, and Poincare disk covers everything.
All right, thank you.
Thanks. Laura, you have a question.
Yeah, okay. Maybe it's more like a comment about the question that has been asked before about non-Gaussianities. It's true that it depends on the scales. So these recent works in single field inflation explore the effect on large scales. The thing is that also at big scales, the non-Gaussianity would have effects. So, for example, on the spectrum, just to make an example, on the spectrum of the second order gravitational waves. We have been looking at these models, multi-field models, polynomial alpha attractor models that have large scalar fluctuation on small scales, and for these models we have found that the non-Gaussianity is large. So yeah, I think it's definitely a topic that deserves further investigation.
Let me ask you then, what kind of models did you study? Did you study this two-field model, like our model? Already checked it?
I did study the original Braglia model that then was connected to, it was made an explicit connection with the alpha attractors. I think you call it axion dilaton. This is, do you remember that? It's a model that you have been looking at. Let's say that you made an explicit connection between that and alpha attractors.
Okay, maybe you send me a reference, or we can discuss by email. My point, which I wanted to make, is that as usual, the answer, usual at least, sometimes answer is very, very delicate and depends on the exact parameters which you study. For example, here in our own model, so many things. Let me just show it to you here. No, here. See, depending on the value of parameter chi0, for example, if chi0 is small, then the whole spectrum, the whole spectrum is concentrated only at the short wave range. If chi0 is just 10% greater, then you go to the range where it is dangerous already. Okay, and if you take it even larger, then you out completely. You have all of these non-Gaussianities and everything, and you screw out all of these Planck data. And the same thing here with constant coupling constant G. So we played with that, and we know that if we take constant G small, then you have this non-Gaussianities and everything. So it's like a concrete study for the model which we have, and we figure it out that if this constant is large enough, then this Isaac curvature model modes, etc., do not produce anything affecting this Planckian range. So it's a concrete question of the concrete model with concrete parameters.
Yes, yes, exactly. But also they would have effect at the peak scales wherever. Sorry, I need to plug in my laptop. At the peak scales, wherever these peak scales are, whether they are closer or further away from the CMB scales, if you have a large amplitude peak and some large non-Gaussianity, that would say something maybe about the perturbativity of that model. So it's not just a matter of how far we are from the CMB.
Yeah.
It could just
yeah. I thought that you're asking a question similar to what was like our worry right now, that you do your calculations perturbatively, you think that you are in agreement with Planck, and in fact, if you study it more carefully, second order of perturbation theory, you just find that this is not. So my comment is that this worry, I do not think that I have right now. Well, at least it is too early for me to worry, because I know how we were able to move the predictions from the infrared to the UV. However, as for the structure of the peak, then it is clear that if the peak is large, at least in this case, if the peak is large, then perturbation theory will fall miserably. And that is why we are happy that if we introduce this parameter D, if we want to suppress this peak and making the effect small, we can have it. So our point mostly was to say that if we want to understand whether the production of black holes is realistic, without pretending that we know everything about it, realistic, whether we can produce very large fluctuations, we do not see at the moment anything that would preclude it. But maybe if we will study this, well, second order perturbations, we will see something, I don't know.
Yeah, it's interesting.
Please communicate with me directly also, I will check. Okay.
Yeah. It's interesting you said that this peak comes from the amplification of the isocurvature mode. So it sounds like it's a local effect.
The peak comes from several different sources.
Okay, yes.
And naively, you would start peak once you have tachyonic instability already, and the position of the peak correlates with this moment when you start instability. But I expected, naively on my side, I expected that that's exactly what happens. And then my collaborators run their program and they say, no, it starts earlier. And then we start, well, seriously communicating, and both of us had learning curve. And now I think that we understand what happens exactly with that, that there are some modes which are, well, isocurvature. They are kind of already prepackaged, and their amplitude can be large enough so they may appear early at the Planck range, okay, at very large wavelengths. And if we want them not to appear, we know what we should do. Because we start generating and we see, oh yeah, actually nothing works, okay? So now we see, you need to choose the proper parameters and then everything seems to fine.
Thanks. Sravan, you had a question.
Hi, Andre. I have a couple of questions. My first question is related to how do you estimate the mass of the primordial black hole in your two-field model, and does it depend on the coupling between the fields?
Excuse me, can you repeat it again?
How do you estimate the mass of the primordial black hole that can be formed in your model, and how does it depend on the coupling between the fields?
Oh, the masses, they all depend on the scale which you produced of this peak. So if your peak is produced at large wavelengths, then you can, well, in general, produce black holes as big as the universe. But our goal is to make them reasonably small. So what is shown on these pictures, that depending on a set of different parameters, and the most important one is this parameter of symmetry breaking, you can control the range. When you control the range, you can make them smaller and smaller and smaller. I do not see any obstacle of producing extremely large black holes, except for when you really go to the limb to produce very large black holes, then you really can perturb the predictions of Planck. But again, for that, we may need to increase coupling constant G. And again, we played with the simplest model which we used. It's just like you take m squared phi squared, hybrid inflation with this m squared phi squared and with quadratic coupling. You can use your coupling as a function of anything. So this is just, well, the simple model which you use, but you can produce a very broad range of black holes. If you want a small, or if you want to ignore black holes whatsoever, because you want to be on a safe ground in terms of predictions, okay? And you do not want to know all details of non-Gaussianity, because it is important for calculation, for studying in detail the process of primordial black hole production. So our collaborators, which are more accurate in this respect, they say, no, let's just focus on production of stochastic gravitational wave background, where we at least, well, do not are not forced in studying non-Gaussianity in such a detailed way and production of black holes. So we gave both types of results in our paper.
Okay, my second question is actually quite very broad. Well, since you motivated alpha attractor models in the context of supergravity, I'm really curious, what is the role of supersymmetry in the context of primordial black holes? Is there any, does it play some role? But I'm just curious.
In this model, if you write the model as it is, forget about supersymmetry. But then if you discuss it with your friends and they told you, yeah, but we really wanted, and that was the reason why we previously had F-term inflation and D-term inflation, and now you forget all of these great models and you produce something non-supersymmetric. And we say, no, okay, these models are supersymmetric, but previously when other sets of models were produced, we did not know many tricks, okay? We just, well, used some simple tricks. Here, for constructing realistic models like that and embedded in supergravity, we needed concept of nilpotent superfield, for example. And there are some special theorems about how to construct the theory, which we were able to derive pretty recently, like 3 years ago. Okay, so they were not known many years ago. So we put, well, this was mostly a responsibility of Renata Kalish in this collaboration. She modestly put all of these efforts in the appendix of this paper and of the previous paper, which we have written with her. So implementing them in supergravity is a non-trivial effort, which was successful only because we learned many, many new things on the way. Okay, but in practical terms, if you don't want to consider supersymmetry, you just, as I said, use normal old Grand Unified SU5 model, whatever. You may just ignore it and you use the model and produce black holes if you want.
Okay, thank you.
Are there any other questions? I think we have time for discussion as well, which we're sort of running into. So if people have questions indeed about preceding talks or issues that have come up there. I think
Yes, indeed, it's just discussion time.
Actually, I have a question to Richard, if I can ask.
Yes. Is Richard still with us?
I'm here.
Hi, Richard.
Hey,
For me, it is still unclear how.
could you speak up? I can't hear you.
Can you hear me? Hello?
Yes.
Yeah. So for me, it is still unclear how stochastic technique has helped you to do the resummation. So can you please elaborate a bit? Why the technique is useful?
Well, for example, it gives us the explicit result for the expectation value of the field phi in the single field model, and also the field A as an explicit function of time. So if we perturbatively calculate those things, we just get a series of logarithms of coupling constants times ever increasing, or a series that looks like powers of lambda squared times logarithm of A. The stochastic formalism gives us a formula where we actually have the full result, the exact time dependence of the thing on de Sitter. And also, since I can now generalize the stochastic formalism to an arbitrary background that's experienced inflation, we can write down what the behavior of the field is in the presence of an arbitrary inflationary background that's experienced primordial inflation. And I gave you a numerical result for what it looked like in that putative geometry that I displayed. So it solves the problem for us, except for a small number of terms which come from renormalization group effects, and those also can be resummed. And indeed, in the most recent paper with Boran Yezeljurt, I did resum them for the exchange potentials of the fields induced by the nonlinear sigma model. And what you find is that the factors, the large logarithms of HR, sum up to be a power of R. And so we have it, So they solve the problem.
And interestingly, maybe one possible application of that sort of stochastic description is precisely to the sort of hybrid models, which Andre, and indeed going back to the paper many years ago, which Andre and I worked on with Juan Garcia Bellido, that phase, there's a phase transition at the end of the initial inflation driven by phi. And in the symmetrical setup, you need the quantum fluctuations to diverge from the unstable local maximum of the potential. I was interested as to whether, Andre has, in the most recent model, has this D parameter to break the symmetry explicitly, but quantum fluctuations
could do that. Something that we could study. I'd be interested to correspond on it if you'd like to think about it together.
Yeah, no, I think, it's something I've thought about in the stochastic formalism, but in practice, of course, one's actually just summing up a whole bunch of terms. But actually, if they become large, you really want to something which can deal with do the resummation for you. Yeah,
that's right. Well, this can do it, and I think this is provably the right way to do it. That is, I think the same proof that Nick Tsemis and I cobbled together of Alexei's fantastic technique for scalar potential models. I think that proof can be generalized to certainly to nonlinear sigma models, and we've checked it at 1 and 2 loop order. We've checked something like 16 large logarithms in those models, and I think the proof ought to be right for that. I have somewhat less confidence that it should apply to quantum gravity, but it looks good. It looks like it should.
So I think, Andre, I would guess that presumably for sufficiently small d anyway, at some point, the sort of class you were sort of talking about the amplitude diverging at phi equals 0, I think, or some, and d avoids that by classical trajectory away from the maximum. At so some level,
what happens if you add this non-zero d? Then the reach of the potential shifts. It's not at d equal to 0. Okay, and also trajectory start bending to the right or left, whatever, depending on d, bending even before it reaches the critical point. So what we were actually doing, in addition just to studying this classical fluctuation, classical equations, we were playing also with this. Just add now a perturbation to classical solution. You may solve classical equation, but you add the perturbation, and what you will see how these perturbations go, and if the sinusoidal waves of these fluctuations may go over the barrier nevertheless, okay? Stochastically, everything like that must happen, okay? The question is how probable. So if you see that it is bending early enough so that this will be the probability of jumping over will be exponentially suppressed, then you feel comfortable that, so in one place it will jump, but then it will produce a tiny domain, and this tiny domain will probably disappear. Many interesting things, though, may happen with this easy disappearing, okay? So it's a subject which is quite fascinating to me to think about, because if you are like on the verge of almost nearly eternal inflation, okay, or if you study really new inflation like SU5, okay, and you do not need this linear term, you actually have topologically inflating monopoles within our horizon, like millions of them. But you have billions black holes which are much heavier, except for if you have eternally inflating something, isn't it bigger than black hole? And it is not obvious that it is smaller or bigger because you need to study geometry of it. So introducing this term D allows you to sleep well because you just kill them all. But not introducing them leads to exciting life. And depending what you prefer, here are your choices. I think that it's pretty exciting to think, and I'm sure that there was a lot of papers, even at the time when we were writing this paper of 96, there were a lot of papers before that of people who studied this temporarily inflating, almost eternal inflation structures like that. So it is interesting to think how it looks from outside. There are some papers on that. It looks like, because it's observational cosmology. If you have a simple, really, what I discussed is very simple model. So if you have really eternal inflation on the horizon, and some people tell you that no, multiverse is unreachable, sorry, it can reach you very hard. So the question is whether you want to study it or not. It's an interesting thing.
Yeah, I think that's right. Yeah. So Ravan, did you have another question you wanted to ask or comment?
I have a question to Andre. So as he mentioned during his talk, so due to Hubble tension, NS can go close to 1. Well, isn't it like, if that is the case, if we can increase the number of e-folds to maybe even 80 e-folds, is it possible? I mean, in single field.
Maybe I misunderstood the first part of the question. Can you repeat again?
Suppose observations say NS is much more close to 1, then we can increase the number of e-folds, right? I mean, the required number of e-folds in the context of single field inflation.
Well, having a number of e-folds is very easy. The question is what you're going to see. And the question how you actually join this H0 to and sigma 8 to Planck. This is all away of my area of expertise, unfortunately. I see what people say, but it seems that we need lots of time to wait. And some of us, and many of you, hopefully have this luxury, okay? For me, it resembles what we had here with this big ship stuck in Panama Canal. Remember? Okay, so it's stuck and that's it. And until it is unstuck, nobody knows what to do. So you prefer for whatever eventuality. So that's why it is good that we have a flexibility to have models producing NS whatever, okay? These models are less elegant, but okay, what is elegant about new dark energy, new early dark energy, newly hot new early dark energy? You need to have engineering to explain what it is. So engineering is not elegant, but without engineering, well, we would not live around. Okay, so yeah, let's wait.
Lara, did you have a comment there?
Yeah, maybe to about Saran's question. So if you can just increase the number of e-folds, well, for a specific inflationary model, in let's say start easy, so instant reheating, actually the number of e-folds is just a number. You need to find it numerically, possibly, and that's a number. And then, okay, you have
scales, Sorry, just you're saying, of course, you're thinking for say the CMB scales.
Yeah, because I think Saran was thinking about what if I just have 1 minus 2 over delta n CMB and I push that delta n CMB to large values, I can approach 1. Yeah, so then you have reheating, and obviously this introduces some of our uncertainties because we're not.
In the reheating, we do not have any constraints, not very stronger constraints on the reheating. So
yes, I agree with you totally. I just wanted to say that as much as you have freedom, which I agree with you, because of this uncertainty of reheating, you can't just do whatever you want with delta n CMB.
But reheating tends to push you in one direction, so it tends to reduce the number of well, let me make that statement anyway. that for simple reheating, it tends to reduce the number of E-folds. So pushing up the number of E-folds is difficult without some. You can do it maybe with some unusual, extra stiff equations of state in the reheating process.
No,
Yeah.
no. What was mentioned, I believe, if you have quintessential inflation with very difficult reheating and a long time, you have this specific equation of state in some models which we studied, you can extend n by about 10, maybe 15, but at least about 10, which is huge.
Yeah.
It's huge. It is that is enough to push NS close to 1.
Well, maybe not
No.
close. I mean, yeah, not. I mean, you could
No,
observe.
not enough.
basically,
Not
but,
enough.
Yeah,
But you know, if the price of pushing NS to 1 is just to study hybrid inflation, it's simple.
yeah. NS of 1 is a simple result in hybrid inflation. Yeah.
It's also interesting, sorry for pushing it forward. It's also interesting that if you have these alpha attractors and you want to deform alpha attractors to get 1, so deformation goes in the following way. You uplift it a little and you start pushing to larger values of NS. You uplift it further, and further uplifting moves you to the area where already hyperbolic structure of alpha attractor stopped working. So you return just to m squared phi squared. At this moment, you have NS greater than 1. And then you uplift it further and you have NS equal 1. So the way to walk from 0.965 to about 1 is 0.965. And then for a long time, it is just like that. Then you overshoot over the 1, and then you return back to 1.
By the way, when you say uplifting the minimum.
I mean, you have m squared phi squared potential. Hybrid inflation uplifts it by the value of the potential at the top of the Higgs potential. Okay. So if the amplitude of uplift is in your hands, it's like a theory. Okay, so if you have a small uplifting, then you have the same prediction as in alpha attractors normal. Okay, if you have larger uplifting, you start increasing, and then at first I did not understand what I see numerically. You get an S greater than 1. I say no, this is not what I ordered. Okay, so when you uplift, you first move away from the range of applicability of alpha attractors. You go back to m squared phi squared, uplifted old hybrid inflation. And there NS is greater than 1. And then if in this model you continue uplifting, then this is a attractor point for hybrid inflation NS equal to 1.
Why is it the case that with this uplifting, you is sort of like large alpha limit?
No, uplifting is the limit such that, I mentioned it in the talk, when you uplift, you increase the term 3h phi dot. Okay, so your field start moving slower. Therefore, 60 foldings correspond not to the distant point somewhere, large value of the field phi, where alpha attractor potential becomes tangent. You still have the same tangent, but your 60 foldings now already, when the tangent is not visible for you in the 60 foldings, so you see only quadratic part. And then suddenly you see a large NS, and then you uplift further, and the friction term increases even more. And then even more, and then you see NS equal 1.
Mm.
It's the same thing, how to travel not moving. We have Zoom. We have uplift.
Well, I think I would be very interested in seeing studying the non-Gaussianities at peak scales for these models that you have presented today.
Yeah.
I think you've got the technology, Laura.
Yeah, I don't know if Andrea, you were connected before. Maybe it was too early there where you are in California, but I presented some work that I done for non-Gaussianity with this multi-field inflation with large scalar fluctuations. And I cannot pinpoint a reference to you because the paper is not yet on the archive, but is basically finished. So I will send it when it's finished.
Yeah.
But yeah,
you may send me your slides, because since you already reported it, your slides are officially not a secret. So you can email me your slides.
Yeah.
Promise not to steal.
Okay. The result though is that non-Gaussianity is large and almost local. So I've studied models where the fluctuations are produced by geometrical effects. So by having in this case you have planar coordinates on the field space. So the geometrical factor is e to the minus 2b1 phi, and that b1 is what tunes the geometry. You can connect it to alpha, but you know that. So for these models, models that are associated with large peaks, the non-Gaussianity is also large, and
this will be non-Gaussianity at the PBH scale or at the Planck scale?
At the PBH scale, at peak scales.
Well, but then this is what you would expect if the fluctuations are of the order 1, essentially. It must be very non-Gaussian.
But no one checked it. No one checked the numbers exactly.
Of course, it's important for the theory of black hole production. It's not
exactly. Also for modification to the spectrum of the second-order gravitational waves.
Okay, thanks a lot.
In fact, because it's really local non-Gaussianity modeling, you see it. In principle, it could be, so maybe you can do the in the local sort of delta n approach. You could calculate actually the full one loop correction to the power spectrum. I think not just with the estimate, but because there's another term from the 3-point function, but actually that's just the third derivative of the expansion with respect to the field. Anyway, so in effect you work out the trispectrum term as well. So I think one could actually maybe even do the explicit calculation, at least on the assumption that it's described by local type effects. But as I said, that seems to be what Andrei was seeing in his model. So the model Laura's talking about is I think it's the polynomial alpha attractor, right? Where it's the hyperbolic geometry causing the two field of the instability in the second field. But it seems from Laura's results that again it's this amplification of the isocurvature mode on large, the amplification on local super horizon scales, which you're also seeing in this. Maybe I think your model is maybe not really. You're not using the hyperbolic geometry there. It's the hybrid models have the tachyonic instability anyway.
In our model we used hyperbolic geometry because otherwise we would not get Planck data.
But if I remember well, you just have for the entire paper alpha equals 1. It's just not that.
In the paper which we issued right now.
So I think David is just saying that it's not the, let's say, geometrical term in the effective mass of the isocurvature that becomes negative and large and makes the isocurvature tachyonic that plays the role in your work.
No, we don't do that. What was strange in this context is that even in the simple alpha attractor model which we have. You see, I placed it there. This well, 3 different pictures because you have just the same set. It just slightly change parameters, and you actually in the second picture, for example, you have symmetry breaking already in the very beginning. So you do not have this tachyonic instability. You just roll down directly to the minimum. And it's the same initial hybrid inflation model. Here, this geometry played an important role. And in the last of these pictures, you do not even have a minimum at all in this picture, because this minimum would, in Higgs potential, because this would be out of this Poincare disk. So this means that your potential starts decreasing exponentially until it reaches, well, infinity. And that is this quintessential inflation or quintessential dark energy, where you get this extra delta n equal 10. So it's very, very strange that you start with a simple model, you try to do something small, and then suddenly the whole world changes.
Can you just go into the action for the Lagrangian for the model that you have discussed today?
Oh, okay. Let me remove here something. This is the one which I have.
Yeah. So this is different from multi-field alpha attractors. After you've done the canonical normalization for the phi field,
here I used the first line shows you this is still not you do not see here kinetic term. The second line shows the kinetic term, and I took non-minimal kinetic term only for the field phi, just for simplicity. It does not affect much unless you really go to the limb, as I said, different things. So it's informative, and this is what happens when you go to alpha attractor already. So these fields are canonical. And by the way, there is one interesting thing, which for me, with respect to this parameter D, I really hated it until I have written it in a dimensional full form, because when you go from one set to equation, massage, etc., you forget how you did it. Okay, so you take the parameter m squared out of the bracket. Long story short is that the proper dimension of this parameter D is mu cube, where mu is some mass parameter. And if you take this mass parameter the same as m, then mu cube will be 10 to the minus 12 or whatever. So this making D small does not involve introducing small dimensional full mass parameters in the theory. You just make mu cube out of that, so that it kind of relaxed my hate of linear terms.
And for this potential that you're writing here, the last line, both phi and chi now are canonical.
Yeah.
Okay. So it's
again here, chi was supposed to be in this model. We took it just canonical to start with. The most important effect came from phi.
I think Laura and I have kind of got interested in the effects of the hyperbolic geometry, although that tends to be for the small alpha models where you have the second field might be the angular field.
That's unfortunately a tricky issue, because in general the models with alpha of the order 1, they are kind of coming natural. I mentioned it this range of this ladder, which I've shown you here. In string theory, in supergravity, they often come of the order one. But on the other hand, who knows?
Yeah.
But
Okay.
this is when you, isn't it these disk models come out when you add additional symmetries, but it's still a supergravity theory for whatever alpha, isn't it?
Yeah. Here is Renata is an expert. Essentially, the keywords are there are some maximal supergravity from which you start reducing everything down. Okay. And in this initial stage, at this initial stage, it is natural to consider disks of a radius corresponding to alpha equal to 1/3. But in this theory, there are 7 such disks. And if you introduce interactions between fields of these several different disks, disks can effectively merge, because the fields belonging to 7 different fields, they start traveling simultaneously. And this changes the effective kinetic term. And this results in effective alpha starting from 1/3 to 7/3. And each time when I'm writing about this, this is what I say, alpha equal 1/3. Each time when Renata talked about this, she said 3 alpha is equal to 1, because because it is geometrical, its curvature in hyperbolic space, it is given by 3 alpha. 3 alpha, it was unfortunate way how we written the first papers, because we wanted others works by like Higgs, inflation, and Stravinsky to be classified and start with alpha equal 1. But fundamental alpha in this research is alpha equal 1/3. But again, if we really think about what happens right now in string theory, for example, and people in string theory, they are already in 2-dimensional de Sitter space living and helping super conductivity people to understand. So difficult field. So no guarantees.
Indeed, I can see in the chat someone was asking, what happens if we work with these theories on ADS space-time? I guess it's well. But anyway, that's the phenomenology of inflation relies on a positive cosmological effect, cosmological constant.
So the quick answer would be in ADS space-time we're all dead. Okay, because the universe would collapse, except for in super string understanding of how you use this concept. It is not a Friedman universe. It is not a Friedman collapsing universe. It's something else.
Yeah.
May I ask you also a question, maybe?
Yeah.
Thank you very much. And surely many thanks for a very nice talk. I have a little bit string-oriented question, because when I try to understand this class of models, I'm always a bit confused. In strings, we have a huge zoo of different moduli fields, of different other possibilities of possible other excitations. How is it common that you select these particular 2 nice fields? And well, then I understand once you select them, you can come to a very nice model, but what drives you to select this particular couple of fields, which then comes to an alpha attractor?
Okay, what I can say is very little. If you look at several different papers which we have written with Renata Kalish and several collaborators a couple of years ago with Yusuke Yamada, etc., we studied, for example, theory of supergravity theory, which is motivated by string type 2B string theory. And in this supergravity theory, we because it's already supergravity, it's already just interpretation of what string theory does. We're just trying to play by the rules close to what string theory does, but we're already at the level of supergravity. And with supergravity theory, we look for minima which preserve supersymmetry. And then when we find this supersymmetry minima, then where do we come with the potentials like that? So the value of the potential is pure phenomenology. It does not come from string theory. So the origin of this m squared, phi squared, for example, you cannot just really associate it with string theory. But what is interesting is that string theory gives you geometry along these flat directions. And this geometry is exactly the geometry which is needed for us. So if we say that along these flat directions, if you do not add any phenomenological term, then it's just a flat direction. But if you say that, well, flat direction never stays flat like in axions, you get something there. So geometry is such that it is geometry alpha attractors. So if you say that along this direction there is something, then if you take something simple, m squared, phi squared, or whatever you take, then you have this potential with nice properties. So there is no really direct link. Here is string theory and do everything in string theory. We are not at this level yet. We're doing it piecewise way.
And when you say string supergravity, sorry, you mean 10-dimensional supergravity?
We no, it's already 4-dimensional.
4-dimensional.
Yeah.
Yeah. So this what is a bit surprising to me. So you say 4-dimensional, so it means that you undergo somehow compactification of at least 6 dimensions, but you simply neglect the effect of all the rest. Well, not really neglect, but you kind of play with the model which you have in hands. Let's put things like this.
Well, then starting point would be to study how all of this emerges, how the compactified space emerges. Okay, so you start with type 2b and find even one way of stabilizing it. So this is something which we suggested how to do like already 20 years ago. And even this part, which was relatively simple, it's so complicated that right now you have an army of people saying that it is wrong and another army of people saying that it is right. And this is before any inflation, okay? So then what we do, suggest you have a theory where things like that are possible, okay? So some minima are possible. Let's try to do the phenomenological description in terms of supergravity theory. So at each stage of this description, you are having part of it as a construction, part of it preserve something from string theory, which is really part of it. And that's geometry, it's kinetic terms, something like that, okay? Doing potential, deriving potentials here is really difficult, except for, as I mentioned, if you are looking in the context of string theory, if you're looking for supersymmetric valleys in the potential, then some theorems can be proven that these valleys really stay supersymmetric. If you start with supersymmetric, they stay supersymmetric, and potential along these valleys identically vanishes. So it is very difficult to stabilize everything, but if you have one flat direction, it remains flat with whatever corrections you add to it. And then you say, oh, whatever corrections, but what if I change it phenomenologically and edit something? So you see that there are many, many dirty steps at each stage. But what we are trying to use some minimal information from string theory, which is, for example, this geometry, okay? So if you have this geometry and supersymmetry, and then we say, and then now assume add something and then miracle happens, okay? So that's incomplete, the theory is incomplete, and so that's what we have.
No, still it's extremely interesting because it's a very nice observation how much you can cook out of just one number alpha here. So yeah, thank you very much.
By the way,
Yeah.
may I ask something related to what Losha was asking? It's actually kind of engineering question in that sense that with this alpha, it's a very elegant kind of generalization of the Stravinsky potential, this kind of departure from there, one parameter. But would it be possible to model this with other curvature terms, let's say R cube, or basically having this quite elegant description of modifying kinetic term? Is it possible to write some function f of r? I'm sure it is possible. The question is, how elegant is it in that case?
Maybe you are talking about two things simultaneously, because I am not talking about Stravinsky model with r squared and r cubed. Or even though what we do looks similar to Stravinsky model, it's not equivalent.
Of course.
No, it's not really. Of course, it's if you start with Stravinsky model and you make transformation to scalar variables, then you have gravity and a scalar field. But if you try to make a tiny change to this theory, like calculate radiative corrections, you never return back to slightly perturbed Stravinsky model. The way is rather delicate. Okay, so if you for example, get this tangent and you say, I want to have tangent plus tangent cube. And way back to these models, probably with Koshelev's tools, adding some richer structures, non-local terms. Maybe one can be translated to each other, but I don't know that. So okay.
I think I understand what Sasha wanted to say.
Oh, okay.
In the sense that Sasha, I tried to do this. I think he wants to find some I don't know, f of r, or let's say some theory written in geometric quantities like Ricci tensor or Riemann tensor or derivatives or whatever, then do conformal transformation and observe phi divided by square root of alpha. I can say that it should be extremely difficult. It will be not elegant at all.
Yes, absolutely. But maybe in some limit it reduces to, so clearly there should be terms like r squared and probably r cube, and maybe one could catch some of these just inflationary predictions in this coefficient in front of r cube.
No, Kuku is not good. It is tested many times, and also we tested with Ivanov, Padiyeva, and Ketov 1 year. It is not. It is very complicated potential you are obtaining.
Of course it is.
But maybe some similar questions about this model. You make some field transformations to get the standard kinetic term, but you can, instead of this field transformation, you can make metric transformations and obtain some models with non-minimal coupling and the standard kinetic term of the field phi. What do you try to consider such types of models that correspond to your alpha attractors?
Yeah, I think, Andrei, it's a question. So basically, Sergey is asking kind of, I think it's a question to you, but it's kind of the same question, just whether it's possible to map alpha attractors just to more complicated non-minimal couplings to
Yes,
R.
it is possible. It is possible. It is. I think there should be one-to-one correspondence between models with non-standard kinetic term and models with non-minimal coupling, right?
Maybe I misunderstood your question, because there may be an answer to this. If you not just say r plus r squared or whatever, but if you ask a question whether it is possible to introduce a non-minimal coupling of phi and r, which would reproduce alpha attractors, and the answer to this is known as positive. Yes, it is possible to modify well, kinetic terms of the scalar field plus a non-minimal kinetic term in such a way as to reproduce with this term all existing alpha attractors. That was done in our paper with Roest and Renata Kalash in 2014, I believe.
If I may comment about the previous question Alexei asked, actually, if you take alpha attractor model and go from Einstein frame to Jordan frame, at least in the case of alpha is very small, you can write an f of r model which looks like r power something plus r square. It was written by a paper by Woodard. So in the limit alpha is very small. That's how f of r model look like, the corresponding to the Einstein frame alpha attractor model.
Okay, thanks.
This slide actually described the construction which we had. So if we have general term, coupling term to R, and general coupling kinetic term for the scalar field phi, if we impose some conditions how you construct these terms, then they exactly reproduce alpha attractors. So if you wish, this just tells you that the theory of non-minimal coupling to gravity is more general than alpha attractors. You produce more structures like than alpha attractors, but even much more. And this is just a particular case.
Yeah, actually, this structure 1 over dividing kinetic term, it usually appears before basically canonification or whatever, canonization.
Yeah.
In this series with non-minimal coupling. Yes.
Yeah, but I'm saying that from the first line of this slide to the third line where you have it, you need these parameters, you need these functions k and omega to have special form.
Yes.
Then you massage them to these alpha attractors. But
right.
Some more general form, you get different answers.
Yeah.
And whether there will be attractors of any time, I don't know.
Yeah, and I think all these 3 types of realizations of alpha attractors will give you slightly different predictions due to reheating. All of them.
I mean, there's a sort of practical thing you want, though, in a sense, for the phenomenological success and fitting the large scale CMB is this plateau behavior at large field values. And so, although you might, here is it given the sort of mathematical prescription for how to relate, different functions. The fact is, to get the effective potential, which I guess here is U, at large values of omega flat, that's not going to occur in general for f of r for general f of r theories, for example. When you link it back to an effective f of r, that's the familiar problem that r squared is very special in that regard. That it's so you need, in that sense, you need your f of r theory to approach r squared at large curvatures to see the phenomenology of the successful phenomenology of Starobinsky, which is shared, more generally within what we tend to call the alpha attractor, the E or T type alpha attractor models. Yeah. So it's different times in different parts of the world. It must be very late in China.
Yeah.
it's approaching. In the UK, we're just heading towards dinner time. I don't know. Do we want to wrap up at this point?
We are at end of the session unless we have more questions.
Okay.
If
Okay,
not, I
thank
think.
you all.
Yeah, I suppose as the chair, I should thank all the speakers, especially those that are left at the end of the session. Thank you everyone for joining in the discussions. The meeting continues early in European time, very early in Californian time tomorrow.
Thank you very much, David, for driving the session.
Okay. Bye, everyone.
Thanks, guys.
Bye.
Very interesting discussion.
Yes.
Thank you. See you tomorrow.
See you.
Yeah, see you all tomorrow.
Bye. See you tomorrow.
Alex, see you tomorrow.